All right. So let's begin. All right.
Very good.
Cool. So good morning, good afternoon, and good night to the researchers in Europe, in Asia, and the US. So my name is Yuanzhuo Yang, a senior at UW-Madison. And today my presentation is about a forklift, an algorithm that generates Zygote trees for faster package initialization. This work was a collaboration between KJ Choi, Kilian Chen, Tyler Carter, and me, Yuanzhuo Yang. This presentation has four parts. First, I will give a brief introduction towards stock containers and Zygote trees. Then I will introduce our Python repository study on real-world data sets. Next, I will explain how the forklift algorithm works, and eventually we evaluate the algorithm. Now I will introduce the concept of hierarchical Zygote trees and how they can reduce the latency of serverless applications. So reducing startup latency approaches can be divided into two categories. First is lightweight sandboxes mechanisms, including containers, virtual machines, and unikernels. The second is initializing process inside the sandbox, like sock zygotes. And now let me explain the concept of sock zygotes and how the hierarchical tree leverage zygote-based sandboxing. For example, if someone called a function that import pandas, we can have a parent sandbox pre-import pandas, and the parent just fork a child to serve the request. Child can further import whatever package they like, for example, matplotlib. The memory pages of pandas are shared through copy on write mechanism, which is memory efficient and isolated. It's also fast because the child sandbox saves the work of importing pandas again. And we can just go one step further. We organizing zygotes in a tree structure. So take this tree, for example, for a request that requires pandas. The leftmost zygote can just fork a child and serve it. For another request that requires NumPy, the root child, which just imported NumPy, can fork a new child and serve the request. And in this tree structure, the common dependencies can be shared. For example, pandas and matplotlib both require NumPy. So pandas zygote and the matplotlib zygote are both forked from NumPy zygote. And I want to emphasize that building such a tree is not trivial. That's why we present forklift. And let me explain this in examples. So for these two trees, should I prefer the left or the right one? Well, it depends on which package is used more frequently. If package F is more frequent than G1, then the left tree will benefit more requests. Now consider a second example. What if G2 relies on F? So in this case, the right tree makes no sense because node 2, which imports F, has a parent that imports G2. Since G2 already includes F, there's no need for node 2 to import F again. And serving the request with a hierarchical tree is also not trivial. If E and F have no dependency relationship, then for a request that requires F but not E, can node 2 fork a new child and serve it? The answer is no, because we assume that package E is malicious. It's a reasonable assumption because malicious packages are everywhere. So attackers exploit type squatting on Python central package repository, where they upload similar named packages to trick user into downloading them. For example, requests and request. And it also happens in Node.js and Ruby. One previous research showed that over 17,000 distinct hosts have unknowingly installed and executed those malicious packages. So this kind of attack never stopped. So in short, any packages in the tree can be malicious, and as long as the request doesn't ask for the package, it shouldn't exist in the sandbox memory. Having seen the challenges of constructing trees, let me give a preview about what Forklift achieves. So with a 640 node tree, it delivers about 5 times speed up in both median and tail latency. Okay, then let's get to the fun part, which is GitHub PyPI dependency study. So before getting into fancy data and plots, let's spend some time on Python dependency management and our dataset. A requirements.txt looks like this. It specifies the dependencies that application requires explicitly. There are other indirect dependencies required by those direct ones, namely NumPy and pandas. Luckily, we don't have to bother figuring out the indirect dependencies ourselves. Pip install helps us install all of them recursively. And as for our dataset, we extract 9,678 unique requirements.txt files from the BigQuery and analyze them. So we first analyze how many packages required in an application, referred to as requirement counts. There are two kinds of dependencies, direct and indirect. So direct dependencies refer to the packages that are explicitly listed in requirements.txt, whereas indirect refer to those that are implicitly required by the project. They are required by those direct dependencies. And to count the required packages, we need to both count the number of direct and indirect ones. So we adopt pip compile to help us. We try to pip compile each requirements.txt to get complete.txt, which contains indirect dependencies and precise package version. I understand that this might be a little bit confusing, but don't worry, I will explain pip compile so that you can understand this slide. So let's reuse the simple requirements.txt example with only NumPy and pandas. So what happens when we run pip compile on this file? Well, it generates an output file. Well, we called this output as complete.txt. You can name it whatever you like. And now we can pass the indirect dependencies from the complete.txt. So the blue-colored packages are indirect dependencies. They are required directly or indirectly by NumPy and pandas. You can even find the dependency relationship just by looking at the comment. So take the package 6, for example. The comment says it's required by Python data util, and Python data util is required by pandas. So we can just tell that 6 is one of pandas dependencies. Another thing that complete.txt tell us is precise package versions. As you see, all the direct or indirect packages in the complete.txt has a version now, and that is generated by pip compile. Okay, so let's get back to this figure. So in this figure, x-axis is the number of packages per file, and y is the proportion of files. There are 3 lines: requirements.txt, which contains only direct dependencies; complete.txt, which contains both direct and indirect ones. Filtered requirements.txt means the requirements.txt that are pip compiled successfully, because pip compile sometimes failed because of indirect file formats. So for a typical application, over 70% of dependencies are indirect, and 10% of the complete.txt files have more than 50 packages. And this means most package requirements are indirect, and package initialization might be much costlier than we expect. We also check how many requirements the TXT files include at least one of the top N packages. So in these two CDF figures, the x-axis shows top N packages, and the y-axis represents the proportion of files again. Version treats packages with the same name but different versions as distinct ones, while non-version treat them as the same. And we find that the top 15 packages appear in more than 50 of the files for both requirements.txt and complete.txt. Further, we measured how often the top 15 packages appeared in the complete.txt file, either grouping all versions of the same package together or treating each package version as distinct ones. We observed that the 6 most popular packages are used as dependencies in about half of all applications. And all of this should suggest that the package usage is highly skewed, which further implies that few Zygotes can provide substantial benefit on code startup. Okay, so now I will introduce how we constructed the Zygote tree using examples, and also how we deploy the Zygote tree in OpenLambda. So the basic idea of Forklift is simple. We construct a tree based on historical call data, and commonly used packages are added to the tree first, and we branch the tree until the number of nodes reach the limit. We also specify a restriction for our tree. Before a package can be imported in a node, all of its dependencies should be imported in the node's ancestors. First, I will define algorithms input and output. So the input includes a binary call matrix consisting of historical call data. So for this matrix, you can say that function 1 requires package A1, B1, C1, and function 1, 2, 3, 4 was each called once. Input also includes dependency relationship parsed from pip compile. For this example, we can say that D1 relies on A1, C1 relies on B1 or B2. Last input is the tree size limit. For this example, the max tree size is set to 6. And the output is just a hierarchical tree. So here is a simple example output. Request for function 1, 2, 3 can be initialized from node 1 as node 1 import A1, which is exactly function 1, 2, 3 are asking for. And for the basic version of Forklift, each node only import one package for simplicity. Now I will start describing the algorithm flow. To bootstrap the tree construction, we add a commonly used package to the tree first. Well, how do we know which package is most commonly used? So we define an indicator called utility. And utility is just the sum of a column. So utilities at root for package A1 is 3. For package B1 is also 3. And for B2 is 1. Since C1 and D1's prerequisites are not satisfied, so we'll just skip them. Because A1's utility is the largest, we see that A1 is the most commonly used package. So we add A1 to the queue first. You can also take B1. It just depends on how you want to break the tie. And after we finish the bootstrap, we will start adding nodes to the tree. Step 1 is to populate the candidate queue. We add node 1 to root, and node 1 import A1, which is just popped out from the queue. After this, we deal with the call matrix. Since function 1, 2, 3 all require A1, these rows will go with node 1. We also set A1 column to 0, indicating that their requirements on A1 is satisfied. So after adding the node 1, we do step 2 to prepare for our future branching. We add the highest utility package at root and node 1 to the queue. Since I have talked about utility calculation, I will just skip the details. So in short, B1 at root and B2 at node 1 are added to the queue. Now we can just do step 1 plus 2 repeatedly to expand the tree until the tree size reaches the limit. And eventually, this tree looks like this. Take request of function 1, for example. It eventually goes to node 3. Node 3 and its ancestors import packages A1, B1, C1, which satisfy all of function 1's requirement. But D1 required by function 3 is not satisfied. This is because the tree size has a limit, and if the tree can grow larger, then his requirements on D1 can be satisfied. So after looking at the basic version of tree generating, we proposed 2 optimization. First is to replace 0 and 1 in the binary call matrix with weight values. For example, import latency. The motivation is that some packages are heavier than others, and putting them in the tree first will be more helpful. And we call this optimization time-based weight. Another is importing multiple packages in one Zygote. The motivation for this is that Python packages often have many dependencies. For example, Python requires 5 dependencies, and Jupyter even requires about 100 dependencies. So we can import a package together with its dependencies just in one Zygote. And we call this optimization multi-package. Since the time-based weight is easier to understand and implement, I will just skip this part and explain how the multi-package optimization works. So the biggest change we made is utility calculation. And it's a pretty complex one. So I just paste function here, which I will explain next. So let me take C1 as an example to explain how to calculate the utility. For package C1, its dependency is B1. So the rows that import C1 and B1 are function 1, 3, and function 4. So we take these rows, calculate the sum on B1 and C1. So the green boxes mark the elements composed of C1's utility. Therefore, C1 has a utility of 6, and it's the highest one. So we enqueue C1 together with its dependency B1 to the queue. Next step is just similar to what we have done before. We start adding nodes to the tree by popping the queue. Now package C1 and B1 are both needed to be imported by node 1, and their columns are also set to 0. Step 2 is also similar. We add the highest utility package at root and node 1 to the queue. So there are C1, B2 at root, and A1 at node 1. And eventually, this 6-node tree looks like this. Packages required by each function are perfectly satisfied. So now we can compare these 2 strategies. The left tree is generated by single package per node restriction, and right side is generated with multi-package optimization. Both tree has 6 nodes. However, in the left side, D1 required by function 3, C1, D1 required by function 2, and C1 required by function 4 are not satisfied. On the contrary, all required packages are satisfied by the right tree, which makes it a better strategy. So after discussing our tree construction examples, I would like to talk about the deployment in OpenLambda. So we choose to deploy in OpenLambda as it's based on SOC containers, and SOC supports a sandbox level fork, which is crucial to our tree. And when the request arrives, OpenLambda performs a DFS-like search in the tree, and the first non-root node encountered during the traversal is selected to serve the request. And I call this DFS-like because it's not strictly depth first. And you will see that in a sec. For example, for a request requiring packages A1, B2, C1, OpenLambda will start the search with node 1. And since node 1 includes B1, which conflict with B2, this node 1 is discarded. Then the search moves to node 2, where B2 and C1 are subset of required packages. So OpenLambda will just search deeper. For node 3, it includes D1. Since request doesn't ask for D1 and D1 could be malicious, node 3 is also discarded. And eventually node 2 will fork a child to serve this request. Okay, finally, I will talk about our evaluation. I will first introduce our workload. The call trees include almost 2,000 unique invocations, and train and test trees are half splitted. We run Forklift algorithm on the train trace and play the test trace on OpenLambda with 5 threads concurrently. So there are 4 variants of Forklift algorithm being tested. So there are basically different combinations of weight policies and whether or not apply single package per node restriction. First plot is about memory usage and throughput. In this plot, x-axis is memory usage and y-axis is throughput. Different color of lines represent different tree construction variants. The different marker shapes represent different tree sizes. We have 2 major findings. First, multi-package optimization is crucial. It doubles throughput compared to single package equivalents. Second is weighting packages by import latency benefit smaller trees efficiently, but the impact diminishes for larger trees. So I also visualized and compared the trees to explain the findings intuitively. Left tree is generated by multi-package, and the right tree is generated by single package. So they both utilize uniform weight. The size of the node represent the import latency of the packages, and the number in the node represent number of modules imported in that node. The left tree has only 40 nodes, while the right tree has 120. And the right tree contains, you can see, a lot of Zygote that import pretty lightweight packages. These containers take up a lot of memory, but provide very little speed up. And here, this comparison explains why time-based weight is a better strategy when tree size is small. Left tree is generated by uniform weight, and right tree is generated by time-based weight. They both utilize multi-package strategy. And in these 40 node trees, the left side contains more. Oh, sorry. I think, yeah, in these 2 trees, the right side contains more heavy packages, such as scikit-learn and NumPy, and it will help the applications to reduce more latency. We also measure the latency on small and large multiple package time-based weight tree. We find that even small-sized multi-package tree can achieve 2 to 3 times speed up in both median and tail latency. And for the larger trees, it achieves about 5 times speed up. Eventually, we measure the tree warm-up time and package hit rate. The Zygote processes are concurrently created with 6 threads during the warm-up, and a package hit is defined as a package which required by functions provided by Zygote. The result is that all Zygote in a tree can be created in less than 7 seconds, even for pretty large trees. And the multi-package uniform weight tree has over 90 hit rate, which is the best one. Okay, in conclusion, we developed Forklift. It's a new algorithm for constructing hierarchical Zygote trees, and it achieves about 5 times faster invocation latency on OpenLambda. And our code is open sourced at these 2 repos. Rackbench is our benchmark suite introduced in the paper. It basically defines interfaces implemented for OpenLambda, Docker, and AWS Lambda. Due to time constraint, I didn't cover it here. So please read the paper if you're interested. Okay, so thanks for attention. Feel free to drop me an email if you have any questions about our work. And by the way, I'm seeking for PhD or founded master position across the world starting next year. So welcome to contact me if you're interested in me or my work. Okay, thank you. So now it's question time. So feel free to ask any questions.
Okay. So, does anyone have questions for Yuanzhuo? Yes. So, can you hear me?
Yes, sure.
Okay, can I ask you a question?
Sure. Sorry.
Yes.
Before, can I know your name first?
What? Sorry.
Can I know your name first?
Yes. My name is Herman.
Okay.
So, as far as I understood, you're running this on a single machine, are you?
Yes, correct.
Yes. But usually kind of open lambda and serverless frameworks or serverless platforms, to be better said, running kind of distributed systems. And also your system is based on memory sharing between, because Zygotes do that, don't they? Like sharing memory between functions basically and sharing a namespace. So just an idea of how could you port this to a distributed system with non-uniform memory access or well, literally different memory namespaces and so on. How could you do it? Or how are you thinking on doing it?
Okay, so let me reinterpret your question. You're talking about how to scale this kind of Zygote tree structure into a cluster.
Exactly.
Okay, so some of my colleagues have done some work on that. I can tell you some part of our work, but not, of course, not exactly all of them.
No.
Okay.
And if you have like
yeah,
privacy concerns, no.
Yeah, I can let you know part of it. So you can come up with different kind of algorithm, like how you can like gather package together in one Zygote, to avoid repeated creation on different machines. That's one way to put it.
Okay.
I don't know if you get my idea.
Yes. Okay, yeah, I get it more or less. Yeah, so no problem. Yeah, if you are currently working on it, so we'll wait.
Oh, it's not me, just my colleagues.
Yeah, just colleagues, but we will be expected for that publication. Thank you, Yuanzhuo. So does anyone have more questions on this? Yes. So I will pass. Did you raise your hand? Okay. Yeah. Sorry. So no one has more questions. As I said before, if you have further questions, feel free to put them or write them in the Discord channel. Okay. So we thank you, Yuanzhuo, once again. We will go on for the next presentation, which is sorry. We have Kilian Müller, is it? And Maximilian Saylor presenting NimbleNet. So yeah, go on. Okay, no, you're using this one. Yeah, just do it yourself. Actually, it was in the desktop. Only put this like here. And I don't know. I think you cannot. Exit. No. Okay, perfect. Yeah, just here. I'll put it there. Should work and make it better.
It looks good.
Does it work? Do you hear me online?
Yeah, I can hear you online, and I can see your first slide, NimbleNet.
Can you see the second one?
And now pretty cool, yes, second slide.
For the audience, do you have a microphone?
Yes, I will share it. That's the moment.
Okay, perfect.
It's around here. I lost it, but yeah, just begin with an angle. What did I do with the second? Right here. Okay.
No, I meant that we have for the audience.
Okay. Yeah.
So I don't have to take more of this one. Do you hear me? Oh no, it's not on.
You have to turn it on. Yeah.
Okay. So, perfect. Okay. Hi and welcome to our presentation. So, NimbleNet, serverless computing for the extreme edge and factory environments. We, that's me, Max, and my colleague Kilian. And as you might already guess from the slides and from the template, we're both from Siemens AG. So before starting into the talk, let's very brief introduction. What is Siemens? We're a quite big company with around 300,000 employees worldwide, and we are active in very different sections. So starting from healthcare over trains, so railway sector, we have factory automation, we have simulation tools, and in the energy sector. But for this talk, only one thing is relevant, and this is the central one, which is factory automation, because we're both contributing to that. So what is factory automation? We as Siemens, we do sell these things, these gray boxes, and that these are PLCs, so programmable logic controllers. And they provide the hardware to deploy software in the shop floor. So they are basically a computer, you could put software on them, and they connect the physical world and the physical assets on the shop floor, which are, for example, actuators, but also sensors and wireless communication. They connect this to the software world. And as manufacturing is probably important for us as a target, and we are from Germany, so automotive is also quite important. We're looking on what is happening there. And over the last few decades, I would say, we see a trend that factories are moving from line manufacturing to more modular manufacturing. That is typically because we get more complex manufacturing processes. We have more customizable cars. That means more configurations. And yeah, this way we get flexible, plus a very tight market situation currently. So also there is the demand for having a more flexible production. So what do these cells look like? The shop floor basically looks like this. So we have cells distributed over the shop floor, and each cell contains one of the PLCs, or typically multiple, more than one. So the programmable logic controllers. Then we have the actuator, which does the job, or also typically more than one. So some kind of robot, milling machine, drilling machine, something like that. We have a sensor which does the perception, or typically more than one sensor, including IoT nodes. So they do the perception, we see what is actually happening there, and connectivity. And speaking about that, for the future factory floor, we assume wireless communication. That is typically because if you want to have a more flexible production and you have everything hardwired, then it doesn't make sense, because adding and removing cells is quite difficult if you have to do the rewiring, which is quite expensive, by the way. And one more thing is, because we don't have conveyor belts anymore, we need something else that does moving around our parts. And this is an AGV, which also requires wireless communication. So speaking about the AGV, what is it? It's an autonomous guided vehicle, and these are driving around in the factory floor and transporting goods, especially the workpiece that should be assembled. It provides connectivity, as said, and we want to talk to it, so it obviously has to provide some connectivity. And for this case, we assume that it will also trigger the workflow on the cell itself. So what does this mean, what's the problem that we are actually targeting? And let me motivate that by a very simple example. So we see the AGV approaching cell number 7, and it tries to execute some work. So it has to load the workload. That could be, for example, this path. Then it travels to the next cell. It loads the workload there. It maybe goes back to the previous cell, does another step where it loads the workload there, and then it finally goes to another cell and executes its workload there. And what is happening is quite obvious. We see that the burden of loading is quite heavy on the 3 lower cells. And we see that these are quite undistributed loads. So we see a lot of nodes that have no communication at all. And we see quite long paths. And this is not the perfect situation. And it kind of motivates caching, what I think is quite obvious. But the question is how? And to answer this question, we looked at how do programs actually look like that we are executing. Typically, they look like this. So we have a loop, and we are starting with sensing the value. So we have a sensor, it does its sensing, and we take the data from it. Then we have to somehow interpret it or evaluate the data. That means we have to convert the blob of data into some KPIs that we actually understand. In the next step, we have to do the interpretation, which is connected to the workpiece itself. That means we have to somehow interpret whether these KPIs are good or bad, or if we have to do something, or what we have to do. And in the last step, we should act accordingly. So if there is something bad happening, whatever that means, we have to mitigate that, and we have to change something. And this is done in a loop over and over again. So let's come back to the example that I presented before. We have now this kind of applications, and it starts with, for example, an acceleration sensor, which does spectrum analysis because we have a rotating device. And that means typically for that, we want to have the spectrum. That means we have to do an FFT. We have the geometrical model, including the oscillation model of the workpiece itself. And with that, we can determine whether we need to do something or not. And of course, we have the driver for the machine. So just as an example, a milling machine here. Then if we have another sensor, which is the typical case, then, for example, a camera here, we need to have the camera driver. We need to understand how to get the data from the camera. We want to do some evaluation, which in this case is also an FFT, because also their spectrum analysis is quite common. We have, of course, the same geometrical model because we have the same workpiece that has to be assembled, and we are still on the same machine. So also this driver is the same. And if now moving to the next cell, we have, of course, a different sensor. Typically, we have a different evaluation model. We have a different machine, so all these things are different. But what stays the same is the geometrical model because we are still working on the same piece. So we can reuse that. And now, if we come back to these programs, we see that there are a few quite common domains. So first of all, we have some hardware-defined things. These are typically the sensing part and the acting part. And these are tightly connected to the hardware of the PLC itself. So it depends what is attached to the device. Then we have our evaluation part, which is algorithm defined. So it's basically mathematical operations. And these are typically connected to the physical values and properties that we are experiencing there. And that also means that, these are typically mathematical algorithms. And we have our workpiece defined things, so things that are connected to the workpiece itself. And from these, we can also quite easily derive some caching domains. So if we are connected to the hardware, we only want to cache, or we want to cache programs on the hardware itself. If we have algorithm-defined things, so mathematical operations, these are connected to the physical layer and therefore to the cell. And if we have something that is connected to the workpiece, it's also connected to the AGV because it's transporting the workpiece. So what is our goal? What do we want to achieve? We want to split programs into these reusable components, and so that we can use caching on these domains. We need to be hardware independent because we have to use our program or our framework on all of our PLCs, which are quite various already, but we also want to include or have to include IoT nodes because of the sensing part. We want to have it simple, and we want to have it transparent for the application. And then then we tried some things that are already there. So we tried micro-containerization, which didn't really work because we often required platform-specific features, and these are typically architecture-specific. We tried Docker, but they just don't fit on the embedded devices, on the constraint devices. And same is true for like all of the package manager that we tried. Plus, they offer sophisticated dependency management, which we don't really need. So what did we do instead? And I will now start with the device part. So those things that are actually related to the device itself. So there we need to be hardware independent. We need to enable simple compilation, and we want to have it transparent to the application. And we do that by using some of the features of WebAssembly. So what's WebAssembly? WebAssembly is a bytecode for a virtual machine. It can be created using LLVM, and that means that it supports out of the box quite a lot of source languages. Then WebAssembly is a bytecode for a virtual processor. That means it can be executed on a virtual processor depending on which mode we select. It can be interpreted, it can be it can be compiled ahead of time and just in time. And because of these features, we get two nice properties of WebAssembly. These are polyglot because we support many different languages. And we have portability because we're executing on the virtual processor instead of the real one. And that means we can execute our program on every device that supports any kind of runtime. And WebAssembly has some more nice features which come directly from the bytecode itself. So the bytecode is a typed bytecode and it's formally verified. Plus the stack machine or the WebAssembly is not able to access the host memory, and therefore we have something what we call sandboxing. And it's optimized for small binary size, which is also quite handy for us. So we have all of these properties: polyglot feature, portability, sandboxing, and small binary size, which nicely fit our use case that we need. But there is one thing that is missing, and this is when we want to split programs into smaller programs, then we somehow have to transfer control flow to the other programs. And that means we need some kind of preemptive execution. And that is not that hard if you're not on a constrained device, but as we're on IoT nodes, we cannot use multiple runtimes at the same time. And that is where we use WebAssembly's import feature. So that means we can import those functions and execute them on any time. And for that, we employ one common host function for all subprograms. And whenever we reach this function, we just need to save the program state. And that can be done by using WebAssembly's feature. So we only have to save the operand stack. WebAssembly is a stack machine. The linear memory, some global variables, and something like the program counter. So we have to remember where we are, plus the binary itself. And whenever we are at that point, we save the current state, then we trigger an error, which will terminate the execution of the WebAssembly module. We can then execute any other function, which might also include hosting another runtime, and can then reinitialize the program and restart it with the program counter decremented by 1. So we are starting right before the host function call. And if we reach the host function call again, we can fill in the pre-saved current values from the previous execution. And by that, instead of triggering the error, and by that we can support preemptive execution. And with that, we have everything that is connected to the device itself. And the next step is to connect everything, multiple devices, and that's the orchestration part, which will be done by here.
Okay, so let's come back to the overall approach. So in the end, we want to have some kind of so we want to have all repeating parts extracted. So we have, for example, some camera functions which directly interact with hardware. We maybe have some kind of algorithm function which will process the images coming from this camera. And in the end, in such a typical flow, we will, for example, store the data. And in between, you can see we will have this kind of code, which is like a top-level serverless function. Of course, we want to reuse those sub-functions. So in this case, we have another workflow. So in the beginning, we have, again, this camera sub-function, which is really, really hardware dependent. In the middle, we want to do some kind of actuator. And in the end, we want to store, for example, the results again. But you can see the first and the last function is reused. And in the middle, you have probably some glue code, which is really specific to the task and can't be abstracted away into the use of the sub-functions. Another good example for the later approach is the following. So you have a neural network. You want to split it up by its layers. So you can load one layer and
so for example, if you might have some function laying in public registry, which then does some overall, for example, sensing of a radar sensor. But on your shop floor, you might employ such a private registry. And in this case, you might have a function which is more tailored to this specific shop floor. So for example, you have a classifier for object detection, for radar object detection specifically for this shop floor. And in the global registry, you have some overall function which does object detection from radar sensors. So now let's see how we acquire those functions in the ideal case or in our mesh setup. So the first thing is that an HEV will trigger function F1. So that's the overall flow in this case. The first thing is that we ask all surroundings or surrounding cells, so our direct neighbors, if they do have this function. So in this case, we can see none of these neighbors has this function. So these requests time out. That's by design to reduce overhead in highly dynamic setups where our setup is also deployed. And so we have to contact the cloud, download the function, and now we have it in the local cache and it can execute it. Now let's have a look how it will look if we have our Nimble functions. So in this case, our function looks like you can see on the top there. We again start with our local cache, want to execute function F1. We acquire our glue code and we see function F1 in this case is not available. But we only have to get this glue code and not the complete function. We will store it locally, start execution, and then we can go to A1. We do the same thing again. In this case, for example, because another flow or another top-level function used this function already, we can go to the right node or to the left node from your side, get this function, execute it, and go to A2. But now we have a problem because the cache of the local node is already full. So we have to evict A1 like this, can now acquire A2, and continue execution and finish execution F1. And all of that is completely transparent to F1. And that's how it's possible, for example, for highly constrained devices to execute function flows which are larger than their local memory. Let's have a look again. So here's a MicroPython example before we come to the evaluation part. In this case, we have just a simple function which gathers some temperature data, and depending on the temperature data, blinks an LED faster or slower. So it could look like this, for example. So first you start executing on the right, on the left here. Then you continue on the top right, execute the sensor code. Afterwards, you will, for example, in this case, blink the LED. This, of course, can also be remote called to another serverless instance. And in the end, of course, you also can replace the whole thing on constrained devices with WebAssembly. That's not a problem here, and you would be even faster and safer on binary space. The implementation is currently done in multiple steps and for multiple platforms. So the first thing is that we support for most embedded devices C libraries where you can execute this code directly or these tasklets. Further, we support all other devices via Docker containers, and all or most other languages are compiled to WebAssembly or are directly supported with MicroPython and Python. The overall setup in this case would look something like this. So in the middle, you would have our mesh setup. On the right and left, so at the network edge, you would have some global or private registries where you can load your tasklets from. And in the middle, all the nodes can share those tasklets in between them, so they don't have to contact for example, the outside of the mesh network, which is probably pretty expensive due to multiple hops being necessary to reach those nodes. But now let's come to the evaluation part. So for our evaluation, we had this simulated shop floor with 20 HEVs, triggering about 9 to 11 top-level functions. And every 10 seconds, they will trigger one such top-level function. And each of those top-level functions is comprised of 3 to 7 serverless functions to show the overall behavior of the network and also the overall approach. So the first thing, what we have seen is that we get, of course, due to caching, more equal utilization of all nodes when it comes to transmitting already used functions and providing them to nodes which require this function now. But we also have seen, of course, traffic increase due to the now more equal distribution on nodes which are far away. For example, let's say sensor nodes, which might be battery powered. So that would be a constraint you have to handle somehow else. Okay, we know that's a bug with the web version of PowerPoint, I think, or with an older version. But what you would have seen is that for overall traffic, so for overall network traffic, we also would have been better. So because you now have this caching locally and also nearest neighbor caching, so you really get lower network traffic overall, but you would see a small hump in the beginning, and that would be until all caches filled up, so to say. Our approach is slightly worse because, so if you don't use our approach, you would only have to acquire one function. In our case, for example, you would have to acquire 7 functions. If those functions are stored directly on the nearest neighbor, then we are faster. But if you have to acquire them, for example, each of them from the edge, then we would be slightly slower, obviously. And the same thing also is the case for response time. So overall, as soon as caches are filled, we are better for many scenarios we tested. What belongs to response time? In the beginning, you see the same phenomena. So in the beginning, we are slightly worse. So it's smooth. That's why we are slightly better. But we are actually slightly worse for the first couple of seconds. But overall, our approach over time outperforms the baseline. We further tested our approach on 2 different testbeds. One testbed you can see here. It's built around Raspberry Pi Zero, so it's a little bit more high power. But we also tested our approach, and from this, the results will be shown in a couple of seconds. On Raspberry Pi Picos, they are highly constrained and only have about 256 kilobytes of RAM. And all of those will connect to a central access point, and we then further emulate our mesh network via software. as you can see, our testbed results also align with our simulation as it should be. So you see that the nodes on the left, which are closest to the network edge, are highly utilized in the monolithic approach. But with our approach, you see that traffic is more equal. But also you have again those extreme edge nodes which are now utilized. So if they're battery powered, that might not be optimal in this case. Now you can see the graphics. I don't know why, but there they are. And you see also that the simulation aligns nicely with the real world. So you see that for send bytes and receive bytes and also for total traffic, we are always better. But obviously that depends on how functions are shared. We just assumed this we tested it with different share rates, so to say. And we have seen similar patterns overall, and also with different binary sizes. So this curve is pretty universal. Again, for response time, also our measurements align pretty nicely with the real world, with the simulation. And overall, we have seen that we are most of the time better than the monolithic approach. But obviously, that highly depends on acquisition time, and this highly depends on link speed. So that might not be the case for all task sets. But in this case, we tested it with very, very small tasks or tasks with very, very small binary sizes. So it is true for most task sets. Obviously, the first thing we now will do is deploy it in a real factory. Even for us, it's pretty hard to come by such an opportunity, but we will try. And the next two things we will do is we will first deploy it in, or we will have a look how to apply it to in-network computing. So in-network computing is just that packages, as they are sent between client and edge server will already be pre-processed by the routers in between. So we can save some latency on the edge server. And another thing is that we want to look how to apply these concepts to in-platoon computing, because all those cars driving in such a platoon or next to each other, in some cases, have to solve similar tasks, for example, for autonomous driving, where, for example, sensors might be different. There might be some higher level algorithms which might be shared, for example. And that's all from our side. And I think we now have a couple of minutes for questions. Thank you for your attention.
A great talk, by the way. The question that's in my mind was that I saw your response time drop, and the difference in response time is about less than 1 second.
Yes.
But when I imagine how it would happen in the shop floor, AGVs carrying things from one place to other, the time scales involved would be like tens or hundreds of seconds, right? So would that actually make that much of a difference?
So that's a good question. Thank you for the question. Obviously, if you, for example, want to carry something from A to B and you have the complete time to carry it from A to B, that's not a big problem, obviously. But for example, if you want to, so the best example, for example, would be you have an AGV driving through the shop floor, and you have to advance your perception of the shop floor, because you have, for example, two AGVs carrying stuff, and they come to an intersection, and now you have to find out, is this intersection blocked or not, and do this multiple times and with different sensors, then it might be critical. That's just for our task set. We know that for our task set, we have a pretty long execution times compared to our response time. That's why this graph look like this. But in the shop floor, it's often critical that you don't have, for example, 500 millisecond response time, but on average, maybe only 50.
Example of serverless I've seen that's truly serverless.
Yeah, it's true. But we try to bring serverless to constrained devices. So it's obviously we are so serverless normally assumes that you don't have access or limited access to the hardware, and you are not limited, for example, to sensors or whatever. So we are probably more into tasklet systems in this regard. But we have seen that especially if we look into domains like, for example, the classification examples we have shown you before, you have like 30 serverless functions, and then you have one function which is directly hardware dependent. So it does not make sense to just focus on this one function. Yeah. Yeah. Mhm. Okay, so about the caching strategies, we have tried multiple, and we have different results. They are not finished yet. So we currently have a look into different caching strategies, also into mathematically proving that, for example, over time, depending obviously on the task set, you get according to some metric, you get an optimal subset of tasks that on each node, for example, which then almost optimally optimizes your, for example, response time. So we currently have a view into that, but this research is not finished yet. Yes. Yes.
Yeah, just talk if you want, Alec.
I will ask that question in Discord. So
Oh,
Yeah.
please repeat the questions. We cannot hear questions from audience for future.
Oh, okay.
yeah, okay.
Okay. Yeah.
Yes. Because the microphone is not for some reason.
Okay.
Know that in advance. So how much can you prefetch? Maybe using a neighbors. You ask, can you?
Yes. 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 So. Oh yeah. Okay. Yes. Sure. I can summarize the question. So it was about if we can. So we know the functions of the function can prefetch them directly before function execution, and not one after another. So we, for example, can improve on response time. Okay, yeah. Okay, so you want to set out the neighbors directly start prefetching functions. Yeah, okay. So that's obviously possible. We did not try that yet. So currently, and this was also the code example earlier, we have. Yeah, I'm kind of bounded, but we have to research it. Yeah. Yes? That is also a nice question, so I will repeat it. It was about, the question was about, are those neighbors direct neighbors? So, for example, ourselves or other IoT devices in the direct vicinity, or
sense to directly send this request via 5 hops or whatever. But currently we are doing it in multiple rounds. So in the first round, we will send it 1 hop. So we ask our direct neighbors. If we don't get any answer, we then send it to all nodes in the same subnetwork. And then we go back to our fallback node and go to the network edge to fetch this function actually. Yeah. But it highly depends on your setup, obviously. Yeah. Yes?
So the question was about whether the preemptive WebAssembly execution requires SDK support. Basically, that's true. We either have to, well, we have to know which functions are shared, so which we have to execute. This requires, of course, SDK support, but you could also do it with code manipulation afterwards. So there is a way, but we didn't test it yet.
Well, thank you very much for your presentation. That was amazing. So now we have Etienne Rivière from University of Louvain.
Switch off the microphones and the audio.
Yes, the microphones are out of battery, so
They switch themselves off.
yes.
Because I'm gonna use my own mic.
Okay, perfect. Yeah. So we can just take it out.
Yes.
And now if you
I just need to. Okay.
you don't need this.
Right. So Alec, can you hear me well? And can you see my background screen?
Yeah, your background is back, looking good. I can hear you well, yes.
Okay. So I also have the mic on.
And now I can see your slide. Looks great.
So I see also if you have questions, you can raise your hands on Zoom. I see the Zoom screen on my. All right. Good afternoon, everyone. My pleasure to be here. This is a work that I did with 2 of my students, Simon and Romain, and unfortunately they weren't able to come here and present, so I'm happy to do the presentation myself. So the work is about energy-aware scheduling of serverless workload on an heterogeneous ISA cluster, ISA-Heterogeneous cluster. So what do I mean by that? What is ISA heterogeneity? Well, in data centers, the de facto standards today and until today is to have x86 CPUs. It could be Xeons by Intel and others. And those are typically CISC processors with complex instruction sets that promise you some high performance per cycle, per hertz. Okay, so they are complex, they consume enough energy. And we also have newcomers, new offerings based on ARM CPUs. Some can be found since a pretty long time on AWS, for instance. And you have more recent announcements by Azure or Google with, for instance, the Axe and ARM processors that you can get and use. And those are RISC type processors with reduced instruction sets, which promise you a better performance per watt. So the question we asked ourselves is, can we leverage the availability of both types of CPUs in the same cluster or in the same cloud to get a better and more efficient use of energy? So the idea is that we have different workloads. They are using different runtimes, different languages, and they may have different behaviors when it comes to the performance and the performance per watt they get on different ISAs. And we wanted to figure out if we could do this scheduling in a smart way so that we have heterogeneous resources that are used better. And the serverless model is really a great opportunity for this purpose. Okay, the serverless models loves heterogeneity because we decouple the infrastructure that will be used to execute functions from the functions themselves. So this allows to have functions that will run either on an ISA like ARM and then on x86 by using a different interpreter or using different virtual machines. And if we have native code, we can actually even compile the function multiple times. The functions are stateless. They store their data in databases, so we can run them interchangeably on the different machines. So running on ARM or x86 is something we want to make a runtime decision. So the research question we've asked ourselves is, can we schedule a serverless workload that is given as an input onto a heterogeneous cluster while trying to match some performance requirements? So we are, from the provider's perspective, we want to match a number of requests per second and per function and reduce the overall energy consumption. So for that, we need to have a way to measure energy consumption. So we need to measure first for the entire cluster, but also for the individual functions, and come back to that. We need to have models that allow us to know what will be the energy and performance profile of a function in order to schedule it in accordingly. And finally, of course, we need to evaluate the approach. So we are targeting actual servers, okay? And that was also one of the starting point of this work. We had acquired different machines that are mid-end. We are talking about around 7,000 to 10,000 euros. And they are with the same characteristics except the CPUs. One machine has two x86 CPUs, two Xeons, for a total power of 350 watts for the CPUs only. And the other has one of these newest ARM CPUs, which you can see here. It's by the company Ampere. And the Ultramax has 128 cores, and the TDP of the single CPU is higher than that of a single Xeon of 250. But the commercial arguments that this company gives us is that it will give you better performance per watt, better sustainability. Okay, that's what we're going to check. So how did we evaluate this? Well, this is our methodology. We have an offline phase to the left and an online phase to the right, which is the actual scheduling of functions. We assume that we have a set of serverless functions. It's given as an input on which we can do offline training in order to characterize them in terms of energy consumption and performance, building models that we can use when we have the same set of functions or a subset of this set of functions and some rates as an input. And we have to decide how many cores of the Xeon machine or the Intel machine and the ARM machine we give to each of them and try to diminish the energy consumption. So we make a few operational assumptions. We assume, as I've said, that the set of functions is known and can be profiled. Okay, so it's a given before. And at runtime, we receive a request rate. Okay, that request rate could change over time, and then we could recompute a schedule, but we know the functions beforehand. We assume that functions run at processes, containers would be the same, and we don't assume particular policies like pre-warming policies that would start functions in advance or keep alive policies that would keep pre-started functions alive in memory for a time. We'll be interested, but we keep it simple. We also consider a high usage scenario. In fact, if we have a low usage scenario, the simplest in terms of energy is to choose one of the two machines and switch off the other. That's not what we want. We want to consider the case where the two machines are necessary to support the workload, and we have to decide smartly on which machine each function should execute and with how many cores. Okay. A result of this scenario is that we have a high degree of function co-location, so many functions will run on the cores of the same machine and may have interferences between each other. Right, so the first thing we need to do is to measure energy. We need to measure how much energy is used, both at the global level, but also at the function level. At the global level, we have access to connected PDUs. This is the kind of device you can see here. You attach it to your rack, and you have access to a programmable unit. It connects to the control network, and you can get the real-time power consumption of each machine or the two machines together. Is there an issue? But that's not sufficient, because when we'll be running multiple functions on the machines, we need also to know how much power is used by each of the functions. And it's not something we get from these PDUs. A process is a software notion. It's something that is built as an abstraction by your operating system. You can know how much power a CPU consumes at a given point in time, that you can get from specific registers and specific tooling at the CPU level, but you cannot get how much is spent by the process. For that, we need to have software tools that distributes this CPU consumption amongst the different processes. And for that, we used a tool that has been here for about 10 years, which is called Power API. Okay, so Power API gives us the fine-grained measurements we need. How does it work? Well, it collects a number of information from the CPU. First, the current CPU consumption, okay, across all the cores, but also a number of hardware performance metrics, okay? That could be the number of retired instructions, the CPU cycles that were spent executing the stalled instructions, and so on. You have so many metrics you can do, and from those, it selects the ones that are meaningful and correlated with performance, and so with energy consumption, and builds a number of models. In fact, it builds models for the different frequencies that the CPUs can operate on, or the cores of the CPU can operate on. And for a given point in time, it takes the CPU consumption and can distribute it amongst the different processes. Okay, so for here, we have 3 processes, and the models can tell us that the first one consumes 50 watts, the second 15 watts, and so on. So this is done in software. It's not our contribution. It exists. It has been built by colleagues in France for the last 10 years. What we did contribute in this paper is the support of the ARM machine. The Power API primarily focuses on x86, on Xeons and other Intel CPUs. So we've built support for the Ampere CPUs by reproducing what is necessary for measuring and redistributing the consumption. So the CPU power consumption, we get it from a small coprocessor that is located on the ARM CPU that allows us to get some low-level performance measurements in close to real time. Okay, so we build support for this. And we get a number of registers, the equivalent of the RAPL registers or the model-specific registers, using a dedicated Linux kernel module. From that, we've built models that allow to allocate the power of the 128 cores according to the different processes in real time. So we know how to measure energy. Now we need to use that for offline profiling. Okay, the idea is to get all the functions that we have in our training set and run them on the different CPUs in order to know first how many functions you can run per second. Okay, so that's simply measuring as a function of time how many functions you run, and also measuring how many watt hours you need for executing those functions. One thing that could come to mind is to run functions in isolation. Maybe I would like to run 20 instances in parallel of a given function without anything else on the CPU and measure performance and energy consumption on that. That seems natural, but in fact, it ignores the impact of co-location. We found out that co-location has a strong impact on the performance, but also on the energy consumption. If you want to have accurate models, you need to take your set of functions that will run together on all the cores and put them with groups of tasks or groups of processes that will share some of the CPU elements. Okay, so what we do is that we take 20 groups, okay, and each of these groups has 8 functions. Well, we had, I think, 22 functions in our data set. I didn't mention that here, but you can use other numbers. And we selectively, we run them onto the different processors to have a degree of collocation. And from that, we have metrics which are, in fact, distributions. Okay, so we have results where we have a matrix that gives us the throughput of a function on a server. So it tells us this function can run 300 executions per second on ARM and 250 on Xeons, or the other way around, but also how much energy cost in watt hour per function the function takes to run on each of the server, right? So this is the models we will use for doing the scheduling, okay? So the scheduling is essentially the problem of taking a workload of functions that were used in the profiling phase and assigning how many cores we'll assign on which machine. In this work, we assign the functions to a single machine. So a function goes either to the ARM machine or to the x86 machine, but not across both, even though it will not be too hard to do as well. So we have our performance models that were built in the previous phase, and the throughput requirements that are the input to our scheduler. It says that this is the number of requests per second that we want to support for this function. We want to go to at least that number. Okay, so we want to allocate a number of cores that is sufficient for this number. We also have the capacity of the machines. Okay, so here the ARM machine has 128 cores, the Xeon machine has 48 cores, and that's the capacity of the two. And the result we want to get is twofold. We have a Boolean matrix that tells that a function goes to a machine A or machine B. So you have a 1 in either column. Okay? And an assignment vectors that tells you how many cores you will have for that function on the processor on which it has been scheduled. So I'm sorry about the slide that comes. It has lots of math, but it's not too complex. We model the scheduling problem as a constraint optimization. Constraint optimization is a problem that takes a number of variables, the inputs, the outputs of your problem, a set of constraints on the variables that are forming the output, and an objective function. And while respecting the constraint, it needs to minimize the objective function. So what constraints do we have? We have the constraints I've announced before. We have a function runs on a single server. So that's this constraint here. The server capacity is not exhausted. We need to use the cores that we have, but not more. And the assignment of cores to function, we can see it here, depends on the energy, the power, the efficiency, sorry, the EIJ here is the efficiency, how many functions you can run per second on that machine for the machine on which the function can be scheduled. Okay, so it means that if a function is more efficient on x86, it might use less cores if assigned to that machine than if it's on the less efficient on the ARM, where it could be assigned more cores if it was assigned to that machine. So this gives us a space of possibility that we will not explore ourselves. We'll leave a solver do that in order to minimize an objective function. So the first objective function is this energy-aware policy you can see here. What does it try to do? It tries to minimize the expected amount of energy you will spend executing the whole workload. Okay, so it sums up over all the machines and all the functions. This W here, which you see is the process level estimation of the power that this function needs. To contrast with another policy, we also have a core-aware policy. And here the goal is to minimize the number of core you use across the two machines. Okay, so some cores will be unutilized. So you simply want to minimize that. And the idea is to see if something that takes into account energy gives better result than something that uses least cores on the two machines, which will be a typical approach that cloud providers will do to maximize the use of their infrastructure. Okay, so we expose this in a solver and we solve it. And for that, we can try and answer the different questions. Okay, but the most important one, the overall question is, can the energy-aware policy outperform this core-aware policy, this policy that tries to minimize the amount of resources in terms of energy consumption? So we'll proceed in 4 steps. First, we'll validate our extension of Power API to ARM. It was a necessary step, which would be one plot amongst many we did to validate this. Then we need to have a workload that is representative of what would run in the cloud as a serverless workload, okay, and encompasses lots of different functions, runtimes, languages, and so on, you'll see. Then from that, we'll run our performance and affinity models. And finally, last but not least, we'll see if the scheduling can improve consumption. Right, so we validated the Power API integration. That's just one plot amongst many, but here to show that it works, we have the machine where we're going to run from 1 core to the 128 cores. And we use a stressing tool called StressNG that simply generates load on the CPU. okay, on each of the cores. And the goal is to see if we have a process level estimation, okay, that matches the expectation. So the TDP of the CPU is 250 watts. We see that we are close to the TDP. We see that when we change the workload, we have a slight variations. Why that? Because we have model recalibrations. Okay, so when the total estimated energy consumption according to the models exceeds the actual total energy consumption, Power API triggers self-calibration, but within a few seconds, we have something that is quite accurately modeling the energy consumption. Okay, so, and as accurately as the Intel machine, which is what matters for us, because we want to have models that can be compared. Right, so the next step is to define a workload. So for that, we use 22 serverless functions. Okay, so in fact, we have functions that are variants of each other that use different languages, variants with different languages and different runtimes of the same function. Okay. The ones in red here are taken or adapted from the CEPS benchmark, which some of you might be familiar with. It's a serverless benchmark, but it didn't cover all the cases that we wanted to cover because it was mostly in JavaScript, okay, and some things in Python as well. We wanted more diversity, so we extended it with some other workloads, okay, some that do some more heavy computation, like matrix computation. And also one thing that is, I think, representative of some workloads in the cloud, which are cryptographic operations. Okay, so we have JWT tokens generation, and also some newer cryptography. This is a system here that we built in the past that does some anonymous credentials. So it is pretty heavy computation on non-accelerated crypto, well, not yet accelerated crypto, that will also be representative because it could be something used in a single sign-on system for identity management. So we cover 4 different runtimes, interpreted, the Java virtual machine, native, and WebAssembly, as has been discussed just before, and 4 programming languages. Right, so let's see how it fares. So we have reproduced here the functions that we have. And on the right, we can see 2 plots. The plot to the bottom is the performance, and the plot to the top is the energy efficiency. And for clarity, I've normalized the two according to the ARM performance. So it means that if the bar, the yellow bar, is below, it means that the x86 is less performant on that aspect than the ARM. Okay. So what we can, and the same applies for energy efficiency, which is the number of executions per watt hour. Okay, if you have more executions per watt hour, then you have more energy efficient. So what can we observe? So first, the ARM machine is pretty damn good. It's actually quite efficient. 21 out of the 22 functions have either better performance or better energy efficiency on ARM than it does on the x86. Okay. The x86 has better raw performance, but not better energy efficiency on only 5 functions. Okay, so that's, and again, the price of the machines, the time of the CPUs is pretty much the same. There is one function that has better energy and better performance on x86 than the on ARM. This is function 11, and this is the image recognition. Okay, it's something that is on Python, but it uses a library that does image recognition. So it's a ML workload on which the x86 fares better. Okay, it might be to differ even better on a GPU, but GPUs were out of consideration for our study. We also see that we have quite some high fluctuations for some of the functions, and that's due to co-location. So here we have these error bars that show you the amplitude of the distribution, and some functions actually are more impacted than others by the co-location of other functions. Okay, so that's also something that might be taken into account. The amount of computations you can do per second depends also on what is running on the other cores on the same CPU. Right, so that leads me to the final point, which is to get the scheduling results. Okay, so here I'm going to look not at the estimation that I get from Power API. It would be a circular argument. I want to see if these estimations lead to power savings at the level of the whole machine. So I'm going to use the global energy measurements at the PDU level. Okay. And I just want to emphasize that the CPU or the CPUs on the x86 machine are an element of a whole. Okay, you also have the consumption of the memory, the network interface cards, and the SSDs and so on. So we won't be, saving hundreds of watts, but we still want to save something. And we have here 5 workloads. So I'm just going to show. So we have, I forgot to mention that, we've categorized the functions in 4 categories. Okay, and we're going to use those categories to form workloads of different kinds. That could be representative of different workloads you would have as a serverless provider. The general one mixes all the functions equally. By equally, I mean that we look at their performance models and we try to assign them a number of cores that is pretty much the same. Okay? Otherwise, if we just use the same throughput, that wouldn't be fair because some functions execute thousands per second, some others execute a few dozen per second. So we try to balance how much load they use. And for the dominated workload, we simply take one of the categories and we make it dominate the workload where 80% of the resources, more or less, are assigned to that category and the 20% for a mix of the others. And we just mentioned that all the runs we did with the results of the scheduler were matching the required number of invocations. We didn't have a case where the number of cores were insufficient for the required number of calls per second. And we're going to look at 5 different policies. We have a first policy that is a round-robin policy. Let's say that you have functions that come in, and you assign them to x86, to ARM, to x86, to ARM, one after the other. We have 2 policies that favor one machine over the other. That would be maybe the most intuitive policy, because when we see that many functions actually are better on ARM, it could say, well, let's fill in the ARM machine first. And when we are out of space, let's use the x86. So this is the ARM first policy that does this. But we also can fill the Intel first or the x86 first, and then use the ARM for the rest. That's the Intel first. And then we have our 2 policies, the baseline optimization that minimizes the number of cores you use, and the energy aware, that is our goal, tries to minimize the total energy consumption. Right, so let's see the results, which you can see here, which are expressed as total watt-hour for a run with the same number of invocations. The first thing we can see is that the round-robin gives the worst results. That's not too surprising, because it completely ignores which machine it uses, and the machines will receive workloads that are not necessarily the best for them. The crypto-dominated actually sees that the Ampere first, okay, the ARM first, sorry, is the worst. Okay, so in that case, even using the ARM machine first gives you worse results compared to a random assignment. If you choose a policy that does ignore models, but chooses one machine or the other first, you don't get very consistent results. In fact, it's either close to round robin, above, below. It's really not easy to say. It does not provide consistent gains on any of the workloads. Sometimes it's better, sometimes not. It's really a matter of luck. The core-aware policy, the one that minimizes the number of cores, has better results than the round-robin in all cases. So the gains are from a small 0.6% to 6.9%. And again, here, I emphasize that this is at the level of the whole machine, not just the CPU. Okay, so there is the baseline of the rest of the machine's consumption that is still there, and the CPU changes by more than that. But when you look at the energy aware, there are cases, 3 in this case, where the gains are more substantial. Okay, we can gain from 5.3% to 15.2%. In particular, the crypto-dominated that has this more heavy processing actually has a better result from the energy aware than it has with any of the others. For the scientific and dominated ones, the results are exactly the same as the core aware. It's not surprising. In fact, both policies will fill all the cores of the ARM machine with the same set of functions. So that's unsurprisingly the same result in terms of energy consumption. Right, so I'm coming to the end of this presentation. So this study has shown that there is some room to improve the performance in terms of energy consumption of scheduling serverless workloads in heterogeneous clusters, even though there is still lots of work ahead. Okay, it's a preliminary in a sense. I would like to emphasize again that our servers are not necessarily the best in terms of energy efficiency, so better hardware can help with the performance not only at the CPU level, but at many other levels. Okay, and we can conclude that the ARM's promise is true to some extent, maybe not to the extent that the cloud provider tells you or the CPU vendors tells you. The gains might not be spending half the energy you need on the more classical x86 machine, but there is some gain to be had. So there are lots of perspectives to this work. First, we saw that there were an impact of co-location of functions, but characterizing the reasons for this impact and maybe try to place functions on the CPUs based, for instance, on their NUMA characteristics and on the hierarchy of resources that are shared, because resources are not shared necessarily between all the cores the same way, would be an interesting topic. The scheduling approach we use is using a constrained programming approach that has limited scalability. You cannot schedule thousands of functions with this, but we think that hierarchical and approaches where you would consider functions by categories and then narrow it down to smaller, more individual functions could be an interesting approach. We also use offline characterization, and we think that integrating the characterization of function in the workflow of serverless model, like when you register a function, run it with representative inputs in order to characterize it, and then use that when the function's called would be an interesting approach as well. And finally, also looking at what's the impact of mechanisms for instance, improving function startup on the energy consumption would be also an interesting thing to look at. And with that, concludes my presentation. I'm happy to take questions. Also, I have them. So if you have questions online, I will also hear them. So just speak up. I will repeat the question to either way. Yes.
Thanks for the presentation. My question had to do with the fact that in this work, power has been equated with like just CPU's activity has been considered for power.
Mm-hmm.
But it has been my impression that memory also contributes significantly to power consumption, and
yes,
it's becoming even more true in today's data center. It's memory
yes,
itself becoming more heterogeneous.
Yep.
So what would be your take
Yep.
on that?
So for the online viewers, so the question is about the fact that this study focuses on the CPU, yet in data centers, memory plays a significant role in the consumption of servers, and what could be done around this. So I think it's a very good question indeed. So there are techniques by which you can shut off memory when you don't need the amount of memory you have on a server. So the two servers we have that have 256 gigabytes of memory each, which we don't need for the functions we run. We actually could use like a quarter of that would work just fine. So I think an interesting take on that would be to characterize also the memory consumption of functions and keep some servers with all the DIMMs, all the RAM on, and keep some servers where it's, let's say, CPU dominated, but not memory dominated to maybe have less consumptions of those. So I think it comes also in the, there is all this trend to server disaggregation where you have the different components that are now disconnected. You could also consider approaches like this, right? Yeah, indeed, it could be taken into account. We don't take it into account in the models here either, but it's the same baseline for the two servers. They have the same vendors, same RAM. So
Are there tools to measure that from the memory's perspective, power consumption?
so the question is, are there tools to measure memory consumption, the energy consumption of memory? Not that I'm aware of, but I'm certain, probably. So the thing is that you can measure lots of things in terms of energy consumption at the device level. So knowing how much a CPU consumes, how much an energy bank consumes, how much your network card consumes, that's easy. Now, distributing that amongst different processes is hard, okay? Because from the memories, I mean, it sees, requests. It doesn't know which process is associated with each request. So that's not necessarily easy. You can maybe look at the working set of applications and divide something, but is it representative? That's a good question.
Kind of similar, the training of the model itself, also this system does consume energy by itself.
Yep. That's a very good question. So the question is, do we consider the energy cost of the training phase in the global energy consumption? So I think it really relates with this point that I'm making here, or what to integrate this in the whole serverless cycle. We know that there are many serverless functions that are called very infrequently. So if you have to spend a lot of energy characterizing them to save a very little, then obviously that's not worth it. So this is really future work, but I think that if we would have to do this, we would probably have to identify the most frequently called functions and only do models for those ones, rather than blindly measure and do the offline profiling for every single function. But yeah, that's a good point indeed. Or there was one in the back.
Considered power capping. There's been some work in HPC workload to show that every bound tasks, you barely just cap the power on Intel and you get similar energy performance to the power, certainly better.
Yeah, so So yeah, good comment. So the question is about power capping. It's a technique that is used in HPC workload when in particular they are memory bound, so that that essentially your CPU doesn't have to run at a high frequency because it's waiting for memory to respond most of the time. No, we didn't use any of that. That's also a very good thing that we could consider for serverless workloads that would be also memory bound. Even though I'm not aware that in the workloads we use, they were not memory bound. They were all CPU bound. Okay? But if we had memory bound workloads, that would certainly make sense. Also, one thing we didn't play with DVFS, the frequency scaling, the voltage scaling. That's also things that we let the default policies of the Linux kernel. We use the same kernel on the two machines and we let the default policies. So we do actually use, so the question is on using the individual energy measurements counters you have. So we do actually get, so the Power API gets all these. It's just that the models are used to redistribute them amongst processes. So it actually integrates all the individual. So it uses these plus the metrics that allow to model the individual consumption of processes. So for instance, on ARM, it was the number of retired instructions, if I'm not mistaken, and two others. And that's, we collect all of these, right? So it's fed into the model, which tells us how much is spent per process. Yes.
Thank you also for this really interesting talk. I was wondering about the levels of energy consumption for the processes where they have 50, 60, 70% energy consumption. It's not a linear function, but only somehow curved.
You measure this and would that make an impact, let's say, to
So-
use the
so-
last 10% of the CPU, because this would not increase the
Ah,
energy
So so the question is about the non-linearity in the energy consumption. Maybe you want to mention a core rather than a process. Yeah, for a core, so a core that is used. So because here we do assign functions to cores. Okay, so of course, because they are called a lot of time. If you actually have, so the non-proportionality, we didn't measure it, but from other studies is that at some point DVFS will come in and you will reach those turbo modes and so on, and that will give you higher energy consumption. Whether it's linear or not, I'm not sure. This is not something I could answer without doing tests, but that's a. Mhm. So if I heard well, it's about functions where the running time depends a lot on the input workload. So that's a good point indeed. So yeah, so we actually considered functions where the running time would be the same. Now, if you have something that does image rescaling and you send images that are 100 kilobytes or 2 megabytes, obviously the consumption will not be the same. In that case, we would need to have models that have another dimension, which is the size of the input. Yeah, that would be doable, but for maybe out of scope for this study. You okay?